Welcome back, everyone, for our online workshop, Developments in Combinatorics. On the second day, we have the first speaker is Chong Shangguan from Shandong University, telling us some open problems in extremal set theory. Okay.
Okay. So good morning, everyone. Many thanks to Hong for the invitation and introduction. So I'm glad to be here. Today I will talk about some problems in extremal set theory. So more precisely, I will talk about cover-free hypergraphs, union-free hypergraphs, and cancellative hypergraphs. So let us begin some basic notations. So we will use the bracket n to denote the set of first n positive integers. So this set will serve as the vertex set of our hypergraphs. We will use n choose r to denote the set of the family of all r element subsets of the bracket n. So an r uniform hypergraph, or an R graph for short, is simply a subset of n choose r, and we will always denote an R graph by H. So next, I will give the formal definitions of cover-free hypergraphs, union-free hypergraphs, and cancellative hypergraphs. So perhaps unsurprisingly, the origin of all these objects dated back to some works of Paul Ehrlich. And first of all, an R graph H is called t-cover free if the union of any t edges does not contain any other edge that is not in this union. Or more precisely, H is t-cover free if for any t plus 1 distinct edges from A1 at and B of H, we have that B is not contained in the union of the AIs. T-cover-free hypergraphs were first defined by a cos and a singleton in coding theory with the name superimposed cos. Later, this concept was rediscovered by Ehrlich, Frankel, and Ferdi with the name cover-free families. So secondly, an R graph is called T-union free if for any two distinct subfamilies A, B of H, each containing at most T edges. We have that the union of the edges in A does not equal to the union. It does not equal to the union of all edges in B. So similar to the case of cover-free hypergraphs. So union-free hypergraphs were first defined by cos and singleton in coding theoretic language, and then rediscovered by Ehrlich and Moser. So lastly, an R graph H is called t-cancellative if for any t plus 2 distinct edges A1 at B, Z of H. So we have that the union of AIs and B does not equal to the unions of the AIs and C. So Ehrlich and Katona studied this problem for t equals 1. And since then, this problem has been studied by many others. The general case, I mean the general T, was studied and introduced by Ferdi only recently. So what are we going to do? So what's the goal of this talk? So we use the three functions ftnr, utnr, and ctnr to denote the maximum size of t cover-free, t union-free, and the t cancellative R graphs on n vertices, respectively. So our goal is to study the asymptotic behavior of these functions as R and T are fixed integers and n tends to infinity. In particular, we will focus on the Turan exponents of these functions. So in other words, we want to know, is there a real number alpha belonging to the closed interval 0 and up, such that so GTNR is of the order n to the power of alpha. So where G is can be any of this F, U, and C. So let us first look at cover-free hypergraphs. So in fact, we already have a pretty good understanding on the maximum size of cover-free hypergraphs. So we call it R graph is T cover-free if for any T+1 distinct edges, so A1, AT, and B. Right? B is not contained in the union of the AIs. Here are the two examples of cover-free hypergraphs. In the first and the trivial example, R equals 1. So it's easy to see that the singletons clearly form a T cover-free one graph for every T ranging from 1 to n. So namely for every T ranging from 1 to n, the singletons form a T cover-free one graph. So in a second example, let's consider the NR, the ceiling of R over T Perkins. So this is an n-vertex R graph with the property that every two edges can have at most the ceiling of R over T minus 1, and hence less than R over T intersections. So note that this value is strictly less than R over T. So in such a packing, the union of any T edges can only cover. So if we take the union of any T edges, say A1 to AT, we won't use the AIs to cover some B. But we know that for every I, the intersection of AI and B, so this size is less than R over T. So the union of T edges cannot cover B entirely because R over T times T is R, and the intersection is less than this number. So so this is in fact the observation of Elish, Franco, and Fruity. A well-known result of Rudolph shows that there exists such packings with near optimal size. So this is proved by Rudolph. So there exists NR, the ceiling of R over T packings. So with size at least 1 minus ln of 1 times n choose this number and divides this one. Okay. So combine this observation and the lower bound of Rudolph. So we have such a lower bound on FTNR, the maximum size of an n-vertex T cover-free R graph. Perhaps this lower bound motivates Elish, Franco, and Fruity to show that such a limit always exists. Namely, they use this function and divide the power of n. So n to the power of the ceiling of R over T. So Elish and Franco and Fruity managed to show that such a limit always exists. And then they managed to determine the limit for some set of parameters. So 2 years later, Franco and Fruity determined such a limit in a fourth generality. So they show that the limit equals to this number. Let us have a look at the denominator of this number. So in particular, the function MR, the ceiling of R over T, comma L. So this is the function M is the well-known Elish hypergraph matching number. So which is the maximum number of edges of R vertex. So here R means R vertex, and the ceiling of R over T graph. So this means the uniformity of the graph, containing no L pairwise disjoint edges. So in other words, this is the maximum number of edges of a hypergraph whose matching number is bounded above by -1. So Franco and Frutti showed an interesting connection between cover-free hypergraphs and this hypergraph matching number. So I think it's a very clever connection. And here, L is some integer that is uniquely determined by R and T. This is not important because it's uniquely determined. So let me say a few more words on Franco and Frutti's result. So I will try to sketch a proof for the upper bound here. So I want to show the upper bound holds. So for ease of notation, let K denote this salient function of R over T. So an L is uniquely determined by R, T, and K. So this is not important. Our goal is to show that such upper bound, if R is T cover free, then its size is upper bounded by N choose K over R choose K minus MRK. So Franco and Frutti basically proved this bound by a double counting. So which do they count? A K subset T of some edge A is called an on K subset of this edge A. If only if T is contained only in A, but not any other hyperedge B. Therefore, observe that there are the total number of cases in an n element and line set is n choose K. So to prove this upper bound, it suffices to show that almost all edges A of H has at least R choose K minus MRK on K subsets. So because this K subset only belongs to A. So if almost all edges have this number on K subsets, the total number of edges should be bounded from above by N choose K divides this number. So to prove that almost all edges has sufficiently many on K subsets, it is equivalent to show that almost all edges has a bounded number of non-on K subsets. So because for every edge, A, so it has R choose K subsets. So we divide the subsets K subsets of A into two parts, on K subsets and non K subsets. And we want to show that the non-on K subsets of A is bounded from above by MRKL. So why is this? The intuition is as follows. So here, this is A. So it basically we want to show that the family of non-on K subsets of A does not have a large matching because this function is the maximum number of K edges in an R graph, such that the matching number is at the most L minus 1. So why the non-on subsets of A cannot have a large matching? Because if the non-on subset of A has a large matching, say has a matching of L, so because this is T1, this is T2, this is TL, these are non-on K subsets. So by the definition of a non-on K subsets, you can find some B1 in H set minus A, such that T1 belongs to B1 and T2 belongs to B2 and TL belongs to BL. So this TIs, the union of these TIs form a large fraction of the vertices of A. So with a little more effort, you can show that if this TI T1 belongs to B1, T2 belongs to B2, TL belongs to BL host. So with a little more effort, you can show that. So A, the set A will violate the T cover-free property. So you will have a contradiction. So they managed to show that almost all edges of A has many on-K subsets. This gives an upper bound on the cardinality of T cover-free H. So this basically, and they are able to show that this bound is basically tight. So although Franco and Fruity have already determined the maximum size of cover-free R graphs, so up to a lower order term, there is still an interesting open problem. So for example, let us consider not necessarily uniform T cover-free families. So this means that the edges in H does not necessarily have uniformity R. So we have no size restriction on the edges in H. It is simply a subset of the underlying set N. So the trivial example mentioned previously, so they are singletons. They form a T cover-free family with size N, which is equal to the size of the underlying set. So this is a trivial example. What are the non-trivial examples? We want to construct a T cover-free family whose size is strictly larger than the size of the underlying set. So we use NT to denote the minimal N such that there exists a T cover-free family with size at least N plus 1. Elish and Franco and Fruity posed two conjectures on the asymptotic behaviors of this NT. The first conjecture, so which is the weaker one, they conjecture that as T tends to infinity, the ratio NT over T squared tends to 1. And their second conjecture, which is the stronger one, states that NT is at least T plus 1 squared. So here is why they think this conjecture is true. Because you can check that a fine prime of order T plus 1 give examples for non-trivial T cover-free families. So where the number of edges is strictly larger than the number of vertices, and a phi prime of order T plus 1 satisfies so NT, the number of vertices, is bounded from above by T squared plus little o of T squared. So this is how the upper bound comes from. So the first known result on this function NT was obtained by in a joint paper with Genninger. So we are able to show NT is at least has lower bound. So the proof is based on Elish-Garlai's exact formula for a MR2L. So which is the maximum number of edges in a graph, not a hypergraph, just a two graph with bounded matching number. So this strange form of this formula so comes from some optimization of these two extremal cases in this function. So yeah, it's clear that this bound is not tight. So now let us turn to union-free hypergraphs. So recall that an R graph is T union-free if for any two distinct subfamilies, so A, B, each containing at the most T edges, we have that the union of all edges in A does not equal to the union of all edges in B. Here is a crucial and well-known observation that connects T cover-free hypergraphs and union-free hypergraphs. So basically, we have if an R graph is T cover-free, then it must be T union-free. So why is that? If a T cover-free graph is not T union-free, so if we have equality here, since AB are distinct subfamilies, there must exist some A belongs to mathcal A, such that A is not in the union of the B. But equality here means that A is contained in the union of the B's. So this contradicts the assumption that the graph is t-cover free. Similarly, one can show that if a graph is t-union free, then it must be t-1 cover free. So since otherwise, if A belongs to the union of, say, I from 1 to t-1 BR, then for these two families, A equals B1 dot 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 BT-1 and B equals B1 BT-1 and A. So these are distinct subfamilies, each containing at most T edges, and we will have equality here. So this contradicts the assumption of T union free. Therefore, based on this observation, the known upper and lower bounds of FTNR give the following upper and lower bounds on UTNR. So the maximum size of an n-vertex T union free R graph. So we have FTNR is at the most UTNR, which is in turn at the most FT-1 NR. So for UTNR, we have this lower bound given by FTNR, and this upper bound given by FT-1 NR. So you can see that the exponents of n, so we always care about the exponents of n. The exponents of n in the upper and the lower bounds do not match for many parameters. So people have tried to improve these bounds. The case t equals 2 has a quite strange exponent. So Frank and Ferdi determined the maximum size of two union-free R graphs up to a constant factor. And Ferdi and Lusingo studied the case when t equals R. When t equals R. So they provide some improved upper and lower bounds for R union free R graphs. So in a joint paper with Zakitamo, we proved a new lower bound on UTNR. So we replace the scaling function of RT of R over T by this R over T minus 1. So we basically show that T union free hypergraphs is closer to T minus 1 cover free R graphs than T cover free R graphs. So and our bound gives exact exponent of UTNR whenever T minus 1 divides R. So we will talk about the idea of proving this lower bound later. So now let us discuss t-cancellative hypergraphs. So here is a recall of the definition. So if an R graph is t-cancellative, if for any t plus 2 distinct edges, so the union of the AIs and B does not equal to the union of the AIs and C. Similar to union-free hypergraphs, cancellative hypergraphs are also closely related to cover-free hypergraphs. So first of all, it is not hard to see that if an R graph is T plus 1 cover-free, then it must be t-cancellative. So since otherwise, if we have equality here, then we will have B is contained the union of the AIs and the C, violating the T plus 1 cover-free property. So with just little more effort, one can show that t-cancellative implies almost T over 2 for cover-free. So why is this true? If the graph is not T over 2 cover-free, then maybe we can find some B, which is covered by the union of A1 A t over 2, and then we can find some C, which is covered by the union of A t over 2 plus 1 A t. So, and this choice of AIs and B and C will violate the inequality here. So you based on the bounds of cover-free families, we can have such lower and upper bounds on t-cancellative hypergraphs. But you can see that, so the exponents of n in the upper and the lower bounds are far from tight. So people are able to obtain better bounds for some set of parameters. So first of all, for t equals 1, people have a pretty good bound on C1 NR. So the lower bound here is obtained by Terherzer. So he applied some method from linear algebra to construct the one cancellative R graphs. And the upper bound applies here is due to Franco and Frutti. So in another paper of Frutti, he obtained good bounds on two cancellative R graphs, which can give exact exponent for C2NR whenever 2 divides R. So in a joint paper of Zakitamo, we can also provide some improved upper and lower bounds for this function. And we can also obtain exact exponent of CTNR whenever 2 divides T and T over 2 plus 1 divides R. So now let me explain how we prove the new lower bounds for union-free hypergraphs and cancellative hypergraphs. So in fact, the two bounds, the lower bounds, this lower bound and this lower bound, can be proved in a unified way by using the so-called sparse R graphs. So let me first introduce the sparse R graphs. For integers, for positive integers V and R, so a sparse R graph or VE-free R graph has the property that the union of any E distinct edges contains at least V plus 1 vertices. So, or in other words, for distinct edges A1, the AE of H, the union of AIs contains at least V plus 1 vertices. So here is an example. This is the final plane, which is a three graph on 7 vertices and has 7 edges. So this graph final plane is 4-2-3 because the union of any 2 edges contains at least 5 vertices. It is also 5-3-3 because the union of any 3 edges contains at least 6 edges, but it is not 6-4-3 because if you consider these 4 edges 1, 2, 3, 3, 4, 5, 5, 7, 2, and 1, 7, 4. The union of these 4 edges does not contain the vertex 6, so it is not 6-4-3. The study of VE-free hypergraphs or sparse hypergraphs was also initiated by Elish in his joint paper with Brown and Soch. So they proved some lower bounds for VE-free R graphs using standard probabilistic method. But we can just skip this because we will use the lower bound of VE-free graphs as a black box. So the strategy is that we use some sparse R graphs to construct union-free and cancellative R graphs. So the lower bounds for VE-free graphs serves as the lower bounds for union-free and cancellative R graphs. So we can view these lower bounds as a black box. So we basically found connections between VE-free graphs and the union-free and the cancellative hypergraphs. So we have 2 results. So the first result says that if an R graph is simultaneously R-partite and TR minus T3, namely the union of any T edges contains at least TR minus R plus 1 vertices. and also TR, 2T free, then it is also T union free. So our second result says that for any integer x belonging to 0 and r minus 1, if an R graph is simultaneously TR plus x, T plus 2 free, and 2R minus x minus 1, 2 free, then it is also t-cancellative. So the proof of the first lemma is slightly tricky. So I will present the proof of the second lemma, which is easy. So basically, we want to show that if an R graph has these two V-free property, then it must be t-cancellative. So assume for the sake of contradiction that this is the R graph is not t-cancellative. Namely, we have t plus 2 distinct edges, AI, B, and C, and this equality holds. Therefore, given this equality, we have that the union of B and C, set minus the intersection of B and C, must contain in the union of the AIs. This is because of this equality. So note that the graph is 2R minus x minus 1, 2 free. Namely, the union of B and C has size at least 2R minus x. This implies that the intersection of B and C has size at most x. So therefore, let's compute the union of these T plus 2 edges. So this is the size of this union can be written as the union of the AI, the size of the union of the AIs plus the size of B union C, set minus the union of the AIs. This is at the most TR, because this is the union of at the most, because this is the union of TR, because this is the union of TR edges. So the union of this of the AIs is at the most TR. And because of this equation, the union of B and C set minus the union of AIs is contained in the intersection of B and C. So this is because this function, this equation. So, and we have shown that the intersection of B and C has a size at the most R. So we have that the size of this union is upper bounded by TR plus X. This contradicts the fact that the R graph is TR plus X, T plus 2 free. So by choosing a good X, we can give a good lower bound for t-cancellative R graphs. So this is basically a proof. So let us summarize the talk. So we introduced the cover-free, union-free, and cancellative hypergraphs. The previous known upper and lower bounds on union-free and cancellative hypergraphs mostly come from the known knowledge of cover-free hypergraphs. So we are able to prove some new bounds, in particular new lower bounds, by relating union-free and cancellative hypergraphs to the so-called sparse hypergraphs. But still, there are many questions left open. First of all, so as mentioned before, what is the minimum n such that there exist T cover-free hypergraphs, so or T cover-free families, so with size strictly larger than n, which is the number of vertices. And we have this lower and upper bounds on the size of UTNR and CTNR. So we can obtain some correct exponents for when R and T satisfy some divisibility condition. But for most cases, we do not know the correct exponents. And lastly, so we want to study the maximum cardinality of cover-free, union-free, and cancellative hypergraphs with no size restriction on the edges. So basically, we want to show what is the largest cardinality of a t-carry-free family. So in which is in the underlying set to the power of n. So what is the maximum cardinality of such a t-carry-free family with no restriction on the size of the edges? So some people think that this to determine the maximum cardinality of these families is a notoriously hard question. So I think my talk ends here. Thank you for the attention.
So let's first thank Chong.
Thank you.